Hello students, today we discuss about the fixed point format. As we have discussed, there are two popular formats of representing numbers in digital signal process. One is called as the fixed point format and the other is called as floating point format. On this basis, we have different types of architectures for digital signal process. First, let us understand some basics about the fixed point format. As an example, if we are considering a 3-bit number which is represented in 2's complement representation. Now, the decimal numbers 3, 2, 1, 0 are expressed in their equivalent binary. The numbers -1, -2, -3, -4, that is negative values, are obtained by taking 2's complement of these numbers. Hence, the number -1 is 2's complement of 0, 0, 1. We can observe that the range of the numbers for 3-bit 2's complement number system is between -4 to +3. This is referred to as the dynamic range for the number. Now this dynamic range happens to be very less in the case of fixed point format. Now, the basic operations for DSP include operations like multiplications and additions, and having a small dynamic range may result in a problem which is called as overflow. Let's take examples to understand this better. Let us consider the multiplication of the numbers 2 and -1. Now each of these numbers are expressed in the respective 2's complement format. The value of 2 is 0, 1, 0. -1 first is expressed as a positive number. Therefore, the equivalent of +1 is 0, 0, 1. We proceed with the operation of multiplying these two numbers. After multiplication, the result you get after adding the partial products is 0, 0, 0, 1, 0. Since we want the answer of -2, we have to take the 2's complement of this result, and we obtain the value after taking 2's complement as 1, 1, 1, 1 and 0. Since we are dealing with 3-bit numbers, if we remove the 2 extended sign bits, we end up with the value 1, 1, 0. And this is corresponding to the answer which is -2, which is the correct answer in this system. Let us consider the value 2 multiplied with -3. Now the representation of +2 and +3 is considered, and the multiplication proceeds in the same fashion. We end up with the answer 0, 0, 1, 1, 0. Taking 2's complement to get the answer in negative, the answer becomes 1, 1, 0, 1, 0. Once again, removing the extended sign bits leaves you with the value 0, 1, 0. Now 0, 1, 0 under this number system is the representation of 2. Hence, the answer which was supposed to be -6 here is incorrect. This happened because of the condition called as overflow. The result -6 is too large in the sense that it is beyond the dynamic range, which falls between -4 to +3 in this example. Now, exploring further under fixed point format, we can also have representations for decimal values which are fractional. Now to obtain the fractional binary 2's complement number system, we shall develop the method as shown below. Let us consider a positive fraction number which is 3 by 4 and another negative fraction number which is minus 1 by 4 as examples. Now 3 by 4 can be expressed as 0 into 2 to the power of 0 plus 1 into 2 to the power of minus 1 plus 1 into 2 to the power of minus 2. 2 to the power of 0 is the weight of the number which is following the decimal point. The weight 2 to the power of minus 1 is the first weight after the decimal point. 2 to the power of minus 2 will be the second weight after the decimal point. Therefore, we believe the equivalent of 3 by 4 is 0, 1, 1. 0, 1, 1. Similarly, the representation for the value 1 by 4 will become 0 into 2 to the power of 0, 0 into 2 to the power of minus 1, 1 into 2 to the power of minus 2. So under this method, it is 0, 0 and 1. To get the answer for negative value, that is minus 1 by 4, we have to take its 2's complement, which is 1, 1, 0 plus 1. The answer is 1, 1, 1. So from this, we have understood the combination of representation, how it will be for fraction. Now, the most significant bit here is conveying about the sign. So the MSB here is 0, it's a positive number. The MSB here is 1, it's a negative number. The remaining bits, they contribute to the magnitude of the fraction. So in this table, we can observe that the value 3 by 4, its equivalent is 0.11. Once again, after the decimal place, we had the weights 2 to the power of minus 1 and 2 to the power of minus 2 respectively. And 0 signifies the number is a positive value. Likewise, it is developed the representation of 3 by 4, 2 by 4, 1 by 4, 0, negative numbers like minus 1 by 4, minus 2 by 4, minus 3 by 4 and minus 1 by 4. Now, these can be actually arrived at from the combination of decimal values, that is between 3 and minus 4. The difference will be that since we are dealing with fraction 3 by 4, you will have a decimal point after the first digit. Now let us discuss about the fractional binary 2's complement number system. We realize that the data here is falling in the normalized range, that is between minus 1 to 1 minus 2 to the power of 2. And this value is equal to 3 by 4. So all your values will fall in this range. The least value you will have is minus 1 and the highest value you will have is 3 by 4 in this numbering system. When we carry out operation of multiplication between two fractions, the result should also be a fraction. Now this concept can be utilized in multiplication to prevent overflow. Let us check out what happens when you multiply the values 0.10 and 1.01, which resulted in the overflow in the previous example. So we take the two positive values 0.10 and 0.11 and we multiply it, and the result we get is as shown below. Next, we take 2's complement to convert that positive answer into negative. the 2's complement is as shown. It is 1.1010. Now, to verify the result, we take the result, and since it's a negative number, obviously the sign is going to be negative. So a positive number could be taken. The equivalent positive is 0.0110, and we can multiply it by -1. It should be the same value. Once again, this is a negative number. You can take the positive form of that number and multiply it by -1. Or alternatively, this could be written as minus for the negative, and the magnitude here in binary is converted to equivalent decimal by multiplying by respective weights. Now we are aware about the weights associated with the different positions. So for the first position after the decimal point, the weight is going to be 2 power of -1, second position is 2 power of -2, third is 2 power of -3, fourth is 2 power of -4. So multiplying the digits with the respective weights, calculating the sum, we get the result as -3/8. This answer is correct, and we can check out from the table also that when you multiply the number 2/4 by -3/4, the expected result is -3/8. Suppose we truncate the last two least significant bits and preserve the 3-bit binary number, then what happens? So in this example, in the result, we are truncating the last 2 bits. So the remaining values you have will be 1.10. Now this is said to be equivalent to the positive value 0.01 in binary multiplied with -1. That is a sign. Or changing to decimal, minus sign, and multiply the digits with the respective weights, we get the answer as -1/2. So in this example, we are looking at truncation. 2 bits have been truncated. Now how much of error will result due to this truncation? Now the maximum error that we will have, or the bound for the error, is said to be equal to 2 power of -2, which is equal to 1/4. Now for this example, if you calculate the error, the value was supposed to be -3/8, we got -1/2. So if you take the difference and take the magnitude of that difference, the answer we get is 1/8, which definitely is smaller than 1/4, which is the upper bound. Now in such a scheme, we can avoid overflow due to multiplication, but we cannot solve the problem of overflow that results when we add numbers. If you consider the example of addition of these two values, your answer is 1.00, which is incorrect because the sign of both the values are 0, means they are positive numbers, but your answer MSB bit is 1, which says it is negative, which should be a wrong answer. So adding two positive fraction numbers is yielding a negative number, and hence this is an example of overflow taking place. As an alternative to representing fractional binary, we have a method which is called as the Q format or the Q notation. The Q format numbers are used in representing the most common method used in fixed point DSP implementation. As an example, to understand Q format, let us consider an example called as Q15. Now under Q15, we are assuming the length of the value to be 16 bits, and the first most significant bit represents the sign of the number, and the remaining 15 bits, they represent the fractional bits. So we understand that here we have the implied binary point, and the weights for the remaining positions are respectively 2 power of minus 1, 2 power of minus 2, 2 power of minus 3, and so on till the very last position, which is 2 power of minus 15. The meaning of the notation Q15 is that we are representing the data in a sign magnitude form in which 15 bits are for the magnitude of the number and 1 bit is for the sign. So the value 15 represents the number of fractional bits we are representing. Now in this case, the number happens to be in the normalized fractional range, which is between minus 1 to plus 1. This particular range is divided into 2 raised to 16 intervals, each having a size which is 2 to the power of 15. The most negative number which can be represented here is minus 1, whereas the most positive number which can be shown is 1 minus 2 to the power of 15. Any result which will happen due to multiplication will fall in the fractional range which lies in between minus 1 to 1. Let us take up more examples to learn the Q format number representation better. Here is an example of a decimal fraction 0.560123. The process of converting it to Q15 is shown here. The process involves taking the value and multiplying it by 2. The product will carry a whole number. Here it is 1. So this 1 is taken to be the respective bit. The remaining fractional bits are taken again and we multiply it by 2. So the number has become 0.120246. We are not considering the whole number, we are taking only the fraction. And this process continues. So the second step yields the bit which is 0. And so is the next one and also the next one. Next we get 1, 1, 1, 1, 0, 1, 1, 0, 0, 1, 0. Now this process is carried a total 15 times. So after performing the operation 15 times, now we got the bits which starts from MSB, which is 1, and it goes down till the last bit, which is 0, which represents the least significant bit. Since the number is positive, the most significant value in Q15, it should be 0. So here is the result that we got: 15 fractional bits and 1 bit representing the sign which is positive. Now in this method, since we are using 16 bits to represent the number, we may lose accuracy after conversion. Like we have errors in quantization due to truncation. However, the error that is generated should be less than the interval size. In this case, we have learned the interval size is 2 raised to minus 15. Now let us check this. An alternative method of conversion is to convert the fraction. So for example, you have fraction 3 by 4. If you want to represent it in Q2 format, we multiply it by a value which is 2 power of 2. So the objective is to convert 3 by 4 into Q2 format. We multiply it by 2 raised to 2, and then the result that you get, it is the equivalent, is 3. And 3 in binary is 0, 1, 1. Now Using the same logic, let us apply it for the data that we had considered previously. So this number we want to convert to Q15 format. Hence, first we multiply it by 2 power of 15 gives you a decimal equivalent which is 18,354. Express this in binary. So the pattern which will emerge after converting it to binary is something which is shown on the right. Now for this number, we are having a most significant bit which is 0 primarily because its sign is plus. So this is another alternate way of converting the number into Q15 representation. In the next example here, we are considering a negative number. So if you are following the process that is described before, you will get an answer which is shown here. First, we are representing it in a positive way, so without the minus. So the positive fraction yields the binary pattern as shown here. MSB is 0, reflecting that it is a positive value. Next, to convert it to minus, we have to take its 2's complement. So 2's complement of the above number yields a result which is shown here. Now using the alternative method, you could take the number and multiply it by 2 power of 15. This yields a negative value minus 5,246.9. We shall truncate the number and represent it simply as minus 5,246. Now once you take its binary equivalent, you will get the pattern which is same as that you got for the previous answer. The next example shows a Q15 sign number which is to be converted to decimal. Since it's a negative number, by inspecting the MSB, we are first going to take its 2's complement and then we multiply the bits with their respective weights and append a sign which is minus 1. Hence, minus is the sign and the remaining bits are telling you what's the magnitude, and it is the answer minus 0.160095. In the next example, we are taking the Q15 sign number as shown and we are converting it to the equivalent decimal. So since it's having a sign bit 0, it's a positive number, we calculate the magnitude from the remaining 15 bits and the answer is 0.560120. To find out what is the truncation error and to check whether it is less than the bound which is 2 to the power of minus 15, we shall verify the truncation error. So the truncation error that you will get is 0.560120 is what we got, minus 0.560123 which was the expected value, and the difference we find is equal to 0.000003, which definitely is less than 30517. So the result of truncation is definitely less than the value 2 to the power of minus 15. If we are taking larger numbers or numbers having more number of bits, then obviously the truncation error will be smaller. Let's talk about addition of Q15 numbers. So the binary combinations are shown and we carry out binary addition and we get a result which is as shown. You can clearly see that the carry has been generated, but in Q15 we have to restrict ourselves to 16 bits. Hence the result is as shown. Now taking the decimal equivalent of that, we get the answer 0.40024. To illustrate the operation of multiplication, let us take the numbers 0.25 and 0.5 as Q3 numbers. The Q3 equivalent of 0.25 will have 3 fractional places and total 4 bits. Therefore, the equivalent is 0.010 and 0.5 in Q3 is 0.100. Now you carry out the multiplication and the result of multiplication will be 0.001000. If we truncate the least significant bits to represent the number is Q3, so we are restricting the number of bits to totally 4 and 3 numbers are in fraction. So the answer we'll get is 0.001. Now this will have an equivalent which is 2 power of minus 3, which is 0.125. We can check with regular multiplication that it is consistent with what we are expected. Now let us summarize some points of the Q number representation. How it is a better choice than 2's complement integer representation. It can prevent what is called as multiplicative overflow. So the overflow due to multiplication can be avoided if we go with Q number format. But there are also some problems with the Q number format. First, when converting a decimal number to its QN format, so N is a general value, it could be 9, it could be 15, where N denotes the number of magnitude bits, we may lose accuracy due to the truncation error. Because we are using limited number of bits, there may be some loss in accuracy. Now this has an upper bound. It is defined by the size of the interval, which is 2 power of minus n. In the case of Q15, it is 2 power of minus 15. Second point, operation of addition and subtraction may cause overflow. When you are adding two positive numbers, the answer may show as negative. When you are adding two negative numbers, you may get a positive number. Similarly, subtracting a positive number from negative number gives a positive number. Subtracting a negative from a positive results in negative number. Number 3. Multiplying two Q15 numbers, the answer is said to be Q30. That is, the number of fractional magnitude bits we get is 13 number. Now, Q30 format will have a total of 31 bits. As we have considered in the previous example, multiplying two Q3 numbers gave the answer in Q6 format, where we have 6 magnitude bits and 1 sign bit. Therefore, in practice, it is common for a digital signal processor to hold the multiplication result using a double word size, such as we have seen in the MAC operation. If you are multiplying two Q15 numbers, the answer will be in Q30 format. There is one sign extended bit, and that sign extended bit is extra, so you can get rid of it by shifting left by 1 bit to obtain a Q31 format and maintaining the Q31 format for each MAC operation. So here's a diagram. So in Q15 number, 15 magnitude bits and 1 sign bit. The second operand is also Q15, 15 magnitude bits and 1 sign bit. The product of length 16 into 16 is 32 bits. 30 bits are the magnitude and we'll have 2 sign bits. So since it's a replica of this same, so this is called as sign extended, we don't need 2 sign bits. So you can get rid of 1 by performing a shift operation, and hence 31 bits can contribute to the magnitude. The problem of underflow can also result in the case of Q notation. That is, the result of multiplication, if it is too small to be held in that particular Q format. As an example, Q2 system, if you multiply 0.01 with 0.01, It leads to the answer 0.0001. Now, to maintain the answer in Q2, the number of fractional bits we can keep is only 2. So this results in answer 0.00, which is equivalent of 0. So this answer that we got is too small for Q2 notation, and hence it's a classic example of underflow. Thank you all.